now. So hello everyone. Today we're going to be going through the OHBM Australia webinar on open science practices for neuroimaging. I'd just like to welcome all of the panelists here and thank them for giving up their time to present, and also acknowledge the traditional land owners and custodians of the Australian lands on which we meet. Most of us are across different lands, but I am situated on the Gadigal people's lands for today. And so just to get started, I'm going to introduce each panelist just before they present their work. We'll run through each presentation. If you have specific questions, feel free to just keep them to the end when we're going to open up for a Q&A for all the panelists and more of a sort of discussion at the end. So I'm going to introduce Dr. Sidhant Chopra. So after finishing his postdoc with Professor Avram Holmes in the US, he's now come back to Australia and is working as a Mackenzie Fellow at Origin, which is affiliated with the University of Sydney. And his work has focused on using neuroimaging analysis and modelling tools to better understand and treat mental health conditions. And he'll be presenting his latest work on reproducible brain imaging figures.
Thanks, Ash. Cool, that's sharing fine.
Yeah, that's perfect.
Great. Hi everyone, as Ash said, my name's Sid. I'm going to be talking to you today about programmatic brain visualizations and sharing some kind of theory, tools, and tips. I am by no means an expert on data visualization, let alone brain visualization, but I think I've picked up some kind of tips and tricks that helps kind of demystify what's often kind of like a dark art of how to actually generate some of these figures that we see in publications. Before I start, I've got a little mini case study. So this figure is a network plot, circle organization, nodes are kind of weighted by size, edges are weighted by transparency and color. This is a really popular plot. You might have already seen it somewhere. And it was from a 2014 publication looking at 10 people who took psilocybin in an fMRI scanner for a resting state scan versus 10, I think, who did not about that. So this figure was extremely popular and has basically been shown in any article to do with psychedelics since then. This was on CNN, and there was probably 100 or so headlines that use this figure. To this day, if there is an article using psilocybin, this figure will be front and center. And it was even used in a submission to both the TGA and FDA to do with psilocybin. And this time they rotated the figures and they messed with the transparency a bit, but it was still used as part of the official documentation. Nowadays, people are just making up random versions of this exact figure and using it to represent psilocybin-based connectivity. And if you drive down Punt Road near the highway, this is an old photo, but exactly where that sign is, you'll see a giant graffiti of this exact kind of network circle plot in Melbourne. And more recently, an organization has used it as an inspiration to make their logo. This is a prominent mental health organization. So there's nothing really inherently wrong with this figure. And the point I'm trying to make is that the figures that we make can really go beyond what we're trying to communicate with our work. So this figure had arbitrary thresholding. It was from a complex derived metric. The authors didn't intend it to be a scientific figure. It was more of a schematic to kind of describe a point in their methods. And the transparency and sizing are kind of misleading a bit. And this is to kind of give you a taste of what we know. There's countless examples of figures that are the centerpiece. The figure itself is the centerpiece, not really the text, the tables, or the code. And we interpret these as scientists, whether we like it or not, rather than the text. And the public and media definitely interpret the figure rather than other contents of the scientific paper. So we need to really think about how we make it, because it does impact the world around us. So I'm going to cover a little bit of quick theory around programmatic brain visualizations or code-based brain visualizations, why they're important and why it's an important path forward as young scientists and for the field in general. And I'll provide you some tips and tools on how to get started with this, as well as improve any skills you already have. And before going any further, what do I mean by code-based or programmatic visualizations? So Historically, what was done often when visualizing imaging data, neuroimaging data, and here I'm going to use MRI as an example, but the principles apply to CT, PET, EEG, other modalities, as well as other organs as well. So individual images are typically opened up in a software that has a graphical user interface or GUI, and display settings are kind of manually changed, and you tinker around until you're satisfied, and this is inserted to a paper. Perhaps before doing that, put into an image processor such as Illustrator or Photoshop to add some auxiliaries such as color bars or change some other settings. Um, there's now a bunch of code-based software packages that are really well documented that don't require a high level of kind of like comprehensive programming knowledge. And here, basically, the figures are generated using code in, say, R, Python, or MATLAB environments. And those are the three kind of more popular ones these days. And what I mean by programmatic or code generated is that you enter code in that language that results in a data object within your environment that can be manipulated or written out as a raster or a vector file, and that's what's inserted into your paper. So in terms of some theory around why, or trying to convince you why this is important, and why using code-based figures can be superior to using GUI figures, one of the main ones is replicability. So there's been a lot of large-scale studies showing that imaging data isn't necessarily reproducible, or imaging analyses and theories are not necessarily reproducible. And one of the solutions that's been offered is to share materials, code, data publicly. And this helps people both verify your work as well as make sure that they're reproducing it correctly. It's pretty rare to see this for figures. It's becoming more popular, but you'll see code for analyses all the time. And journals that require code for papers that you submit, you can get away with not giving figure code these days, right? So if you do provide code for your figure, you're actually following principles of open science, and you provide a direct and tractable link between what you're putting in your paper and the data that was used to generate it. Some people, there's a famous blog that basically said, if you're publishing figures without code, you're advertising, you're not really doing science. And that's a bit extreme, but people do think of it this way, right? If you're just publishing these artistic figures without actually having a tractable link back to the data that was used to create them. There's obviously middle ground alternatives to this. You know, most GUI tools, or a lot of GUI tools, offer batch scripting or some sort of terminal interface, and they're equally reproducible. So they're a great middle ground, but they're also idiosyncratic. They're kind of neuroimaging specific, and they don't give you transferable skills, and they can be hard to reproduce unless the person doing it is also familiar with that particular GUI-based environment. And the other problem with these is you don't gain the next two advantages that I'm going to talk to you about. And the first one is you don't gain flexibility and scalability. So when you're generating figures using code, a simple for loop allows you to make modifications really easily and generate figures en masse. So if you have a request from a reviewer or an annoying co-author to change something, you can do it pretty easily and see the end results immediately, right? You can explore multiple color schemes, make multi-panel figures quite quickly when using code. The gains for practicing this stuff and learning it is cumulative. The more you do it, the better you get. You can develop a personal code base of different ways of doing figures, and you can use this across multiple projects. And I'm sure we've all seen papers where you instantly know which group they came from because of color schemes or figures they've used, right? And this is because they've developed a code base for visualization. I'm not saying that's something important or noteworthy. It's just potentially one of the advantages of focusing on generating programmatic figures. And these skills are really transferable, and I'll get into this later, especially if you're working with common imaging engines such as Matplotlib, ggplot, or Plotly. These all have brain visualization tools linked to them now, and you can gain pretty transferable skills that go beyond just brain visualization to data visualization more broadly, as well as just data science and data analysis as well. And often these days with big data sets, biobank, soon all of us as well, the images are not just the end result, they're often used for QC and big data, for quality control, right? And this is kind of impossible unless you're making programmatic figures, right, to generate images for quality control at different stages of the analysis. And by doing this, you can actually reduce errors in your data, being able to visualize these large data sets. Because if you don't know how to do that, people usually skip that QC step. So this actually opens up the door to being a little bit more rigorous with quality control. And I think the final theoretical advantage is that a lot of people use code for and scripts for analyses, but not for brain visualization. That last part is usually outsourced to a different tool. And this breaks the integration and flow. And there's a lot of research in software development to show that there's a switching cost. As you're switching between environments and screens, you're much more likely to make an error. So having the data visualization built into your analysis script really makes you less likely to produce errors. And it also gives you immediate feedback of the end result. Right, the figures updated real time. So when you're making modifications, the end result is visible and changes are visible. So you can kind of keep track of that. And before, I said there's a difference between science and advertising, but often in science, you do have to advertise your work. And having an interactive or dynamic figure, which usually code-based visualization tools allow, really draws attention to your work. And speaking from experience, a flashy figure will get you more media traction than like a triple replicated finding where the main output is a table. These sorts of figures do draw attention to your work, and journals do allow you to embed these into your work. The data we work with is inherently 3D or 4D, so choosing the right angle or the right slice is a difficult thing to do, and there's been a lot of research showing that this can be quite misleading. But you can embed rich data into papers if you've written it by code. And this isn't just gimmicking anymore. This has been around for a while, and initially wasn't really used, but nowadays even big medical journals like the New England Journal of Medicine actually allows you to embed figures. And recently there was a big study on an amyloid beta clearance drug, and the results of it were actually embedded as a nifty in the paper. So this is being picked up by mainstream journals, and it's actually quite useful. So in terms of some practical tips, I think the first tip is to go across and read some practical guides, especially if you're a beginner. This is more so for people, newer researchers. And there's 3 main guides, I think, in the field that can help with this. There might be more that I've missed, but these are the 3 that I've used. The first one was by Christopher Madan a little while ago, and it's less so about programmatic visualization, but more about 3D mesh visualization. So especially if you're trying to visualize difficult or non-atlas based regions, such as brainstem regions, or subcortical regions, this provides you a really nice guide on how to go, and I'll provide these slides later, how to go from a nifty file into a 3D object. And it's a bit dated, but I still refer to it because there's really nice methods from going from a 3D voxel based image to a mesh based image. The next one is something we wrote last year, which is a didactic guide for beginners to select the tools required to do these visualizations. And I'll get into this a little bit more on the next slide as well. But again, it's focused on MRI, but the principles I think apply to a variety of modalities and organs. And the final guide came out a few days ago, and this was a continuation of our work. This is by Maxim Chamberlain's group, really focused on the different tools available for diffusion MRI visualization. And this was a bit of a gap in the field. And I thought it was a gap, but this beautiful summary covers all these tools that are lesser known and hard to find on how to actually visualize tractography data in a variety of different ways. So the guide that we published is, as I said, beginner friendly. And the idea is to break down the steps required if you see an image or if you have an idea how to actually get there in terms of brain visualization. What are the advantages of using R versus Python? If you have a vertex or edge level visualization, what are the tools available that will actually produce that, as well as some tips on how to share these code, basically. The second main tool is a tool selector that we provided in the manuscript. And by that, I mean, it's just a table. It's a table of 100 or so packages, tools, or libraries in R, Python, and MATLAB that is broken down by the type of visualization, vertex, region, edge, streamline, as well as the input for that, to visualize that. So if it's a text file or a nifty file or a gifty file, as well as links to these tools. And They're specific to R, Python, and MATLAB environments, and there's tools that go beyond that. And when I first presented this, the people at AFNI were a little bit upset because AFNI is a beautiful collection of tools, and they do have visualization functions that were not included in this. And the idea is to encourage use in established programming environments to give people transferable skills. Um, but that's not to say that the AFNI visualization tools are not widely used and excellent, but this table doesn't necessarily cover everything outside those environments. And you can add your own tools to this. I'll give you the link at the end, but there's an interactive form where if you develop a tool or find one that's not on there, you can enter it in this table, will automatically update with that information as well. And Maxim's group recently did the same thing, but with diffusion MRI tractography specific visualization tools. Again, a lot of these are not programmatic. Nonetheless, they do provide a staggering range of functionality to do with tractography, and they can produce some really accurate and beautiful images. So the table can be a bit hard to navigate, so we've created an interactive version of this table. So if you wanted to say, find Python tools that are specifically visualizing regions or polygons, and the input data that you have is a text file or a CSV file, you can kind of click through and select those, and it'll provide you with a list of potential tools. I've even put a little indicator to which tools might be more beginner friendly, and you can switch languages to R and see what's actually available there. And again, if you find tools, please add to this, and if I've missed some, it'll be really good to include them here as well. The final tool is a code template generator. So this kind of came from constantly being asked how to do brain visualizations. So I made this it's a little bit janky, but it's been used for thousands of hours by hundreds of people. So there's obviously a need for it. And the idea here is, and this is just for R and Python, you use a GUI to do some basic selection of options. Like I want to make an edge level diagram where the nodes are weighted by degree or something like that. And you can select some very basic GUI options. And at the bottom there, it will provide you the code in R or Python that can be pasted in, and then you can use that to actually generate your own visualizations. So this is incomplete, where we've done that by design, where this won't work out of the box. You're forced to actually change some settings, some input data to actually learn how to use this. And each of the code blocks that is pasted out has links to the tool being used, so you can understand what else can be done with this and how can I take this further. So being programmatic is definitely a spectrum. I use GUIs all the time, and all of us do, because they're fantastic for quick single scan visualizations, especially if you want to really dig into anatomical specificity, being able to interact with it. And there's obviously ways to do that in programmatic ways as well, but it's much easier with a GUI, so they're still quite useful. I use them all the time. You still cannot do complex multimodal visualizations using code, right? You can't make figures like this just using code. I don't know, maybe Sina can, because I see he's been playing around with Blender and a few of these kind of Hollywood level CGI visualizations. So it might be possible, but it's quite hard. So I think using a mix of GUI and code for really complex visualizations is still absolutely necessary. I still use imaging processing software such as Photoshop and Illustrator occasionally, because complex multi-paneling is difficult still using code. Also, visual auxiliary adjustment, such as color bars and specific labels, can also be a little bit difficult, although not impossible. And I'll finish with, where do the current tools fall short? So, as I said earlier, fine adjustment and auxiliary is hard. Exact placement of labels and color bars, it can all be done programmatically, but it is hard. So, it's okay to outsource these things as long as the core of the data is still programmatic. You can work your way up to actually doing it fully programmatically. There is a solution to this. Focus on tools that are based on established engines, such as Matplotlib, Plotly, ggplot. These tools already provide ways to do really fine fiddling of visual auxiliary. So I tend to use those tools, and I've marked them, I think, in the table selector if you want to focus on those. And also, like I said, provide those transferable skills to general data visualization and general data science. there is still a corticocentric bias in a lot of these tools where they're really focused on cortex. So visualizing subcortical or subtentorial structures is still hard. You really need to go to customized mesh-based software, PyVista is an example, but it's still hard. Diffusion-based tractography, as I said, there's a lot of tools available in terms of easy to use, accessible programmatic tools like you have for cortex and network visualization. They're still not there, although I know there's a couple of tools being developed for that. And there's one tool that just came out that claims to solve it all, and it looks absolutely fantastic. So this is from Russ Poldrak's group. It's called Hive, and the idea is to use the same, I guess, backend or primitive or geometric primitive to visualize surfaces, nodes, edges. It's all the same. And it's based on something called PyVista. It's a Python library. This is a Python-based tool. It does look like it has a tremendous learning curve. I've only played with it for a little bit. It is promising, but hopefully a tool like this will kind of eliminate the need for a table of 150 tools where it kind of brings everything together into one platform. So I've hoped for this particular tool. And I will finish there. I'll say thank you to the co-authors of that practical guide work, as well as the Neuro and Helga Cooper Foundation, who funded this initially, and recently the Biological Psychiatry Australia, who are funding the server costs and everything for those tools that I've shown. And yeah, I'll finish there. Thanks.
Great. Thank you, Sid. That was a lovely talk. And I loved the little videos throughout. It's very interactive and easy to follow.
The GIFs are good because the live demonstrations, it's just a bad idea.
Yeah, it's perfect. I really gotta get bored on doing the GIFs. I've seen other people in the group do it, but I'm yet to sort of cross over the bridge. All right. So now passing on to our next speaker, we've got Dr. Sina Mansour, who is a postdoctoral fellow with the Computational Brain Imaging Group at National University of Singapore and the Melbourne Neuropsychiatry Centre. And his work has focused on computational models of brain connectivity and then implementing these models to better understand individual differences in brain connectivity and psychopathology. And he's going to be presenting on some of his experiences in implementing these reproducible tools.
All right. Thanks so much, Natasha, for your introduction. Just to make sure, can everyone see the slides?
Yeah, that's perfect.
All right. Wonderful. Okay. So after a bit of thought, I prepared the talk like this topic for the talk, which is basically open science for reproducible neuroimaging prospects and realities. And I mainly aim to discuss about all these interesting directions that open science does provide to us researchers, but also some of the burdens that may probably be good to know prior to starting your work with using these open science tools. Now, before I start, what is open science? Well, it's mainly about transparency, sharing, and inclusivity in our research. And it serves a lot of different aims, but mainly the aim is to democratize access to our research, to promote equitable resource distribution and foster accountability, trustworthiness, and ideally to improve reproducibility and rigor in our results. And in order to do that, there are a lot of components to open science. There's open data, open code, preprints and publications, open source software, infrastructure, and having a brief look at the overview of what open science actually consists of. The first thought that comes to anyone's mind is yeah, sure, but why? If research is still working and this requires all this amount of extra work, why should I really spend the time required to understand how to work with all these new aspects of making my science open? And the idea is that, first of all, there are many advantages and benefits to open science. Yes, there will be some time and effort required to accomplish all the optimal settings with regards to open science, but every single step gets you closer to getting some of these advantages, which include, first of all, increasing reproducibility, which in neuroimaging and neuroscience research seems to be a problem that is still not fully addressed. And we have some reproducibility crisis in that, like, you see a paper, but you find hard time actually reproducing some of the results. So by making data and code accessible to everyone, you allow others to verify and build on your results faster. And that's the second point, which is like it accelerates scientific progress. So whether it's you benefiting from other people who provide their code and data openly or others benefiting from you, it will nonetheless accelerate the scientific progress. It would also enhance your credibility and the trust in your work. So when you openly share what you have found, usually the community is more open to accepting the results, and it leads to a broader impact of your work. So basically, at the end of the day, as researchers, we would be interested for our work to be seen, to be cited, and to be used. And open science has shown in several studies that if you basically try to do open science, you usually get a higher impact out of your work. And personally, I believe another aspect of it that is less discussed is the collaboration and networking. In my own experience, doing open science usually leads to interesting collaborations. You get to know people all around the world who are interested in similar prospects and ideas in open science, and you get to build your own network, which can foster collaborations and lead to partnerships. So that being said, what do I plan to cover in this presentation? Well, first of all, I'll try to go over some of the specific aspects of open science with particular focus on things that are most relevant to either students or early researchers. I will try to introduce different tools and resources that actually would come in handy, I believe, particularly for beginners, but also I have tried to include like different level of stuff that people could do. So some of them are more attained to those who are new to these concepts, and some other tools or resources may be beneficial for people who have some previous experience with open science. Now, without further ado, let's dive deep and see what these different aspects of open science are. We obviously are not going to be able to cover all of them, but I thought that like I could cover some of the main ones that early career researchers or PhD students would face in their day-to-day work. And the first topic is open data. So open data is basically about making your research data publicly available for reuse, allowing others to verify your results, run new analyses using your data, and also integrate your data in their own work. Obviously, that being said, neuroimaging data in particular cannot always be open in the same sense as many other data. There's always the ethical side of whether we are actually even allowed as researchers to provide this data completely openly. And there's also usually a lot of rules around how open a data set can be. And when you're using an open data, you need to respect those rules. But generally, there are two sides to open data. On one side, you utilize the data that is openly available out there, and on the other side, you may be thinking of providing your own data and contributing to a new open data resource. So I'll briefly discuss these two aspects and cover some resources that might come in handy if you're intending to pursue providing open data or utilizing open data. So when you want to utilize open data, there are several neuroimaging, neuroscientific data sets out there. So it usually helps you use data from one or multiple, a combination of those resources, and formulate novel research questions. In my own experience, open data has been invaluable in that sense. Basically, literally, none of my research would have been possible without the generous contribution of others who have provided open data to the field. So I would highly recommend, if you're having a problem of interest, a research question that you want to tackle before even thinking of maybe collecting data yourself, try to see if there's some open data out there that could be used to somehow address your question or come up with a solution without the need to actually collect data. But it also is important to note that many open data sets out there, despite of being termed open, usually require formal applications, and there's some due processing until you get your hands on the data. And particularly if you want to do a large scale open data research, which requires access to multiple data sets, it's important to keep that in your timetable. It's gonna take a considerable portion of your time just requesting access to those data sources and acquiring those data before even having the opportunity to analyze anything on the data. But so there's obviously so many different resources out there, most of which are like to some degree open, some of them more open and some less, like the UK Biobank in this list. Some people even argue if at its current stage it's really open. There's a pay to access fee, and then there's also all these other constraints around it, but several other data sets also out there. You simply have to submit a request, and within a few days, you have access to hundreds, if not thousands, of brain imaging data. So feel free to get a screenshot of this because there's so many things, and I might probably have left a lot of interesting data sets out of here, but I'll also share the slides afterwards in case anyone's interested to have a look. And basically, the other aspect of using open data is contributing data, which again promotes transparency. It helps with collaboration and increases the visibility of your research or paper. And you might be asking, okay, I've done this analysis in what different ways can I provide the resulting data back to the public? And there are different levels in which you could provide your data back to the public. At the very basic level, you can provide some summary data like demography information or IDPs through general open data services out there, things like Zenodo, Figshare, and the OSF framework. They all provide you with the basic free utilities that you can basically host your data in a public resource as a public resource, and then others could access that data later on to verify your findings or make use of your data in their own research. Now, there are also two specific types of data that are mainly for neuroimaging studies. One is brain maps, so whether it's statistics, whether it's task activity maps, or any sort of spatial map of something happening on the brain. There are mainly two tools that I can think of, NeuroMaps and NeuroVault. They're both, first of all, repositories of such maps. So you may want to check them out and see if there are any interesting maps on those services that you want to use in your own research. But they have also provided the ability for you to request for your brain maps, the brain maps from your study to be added onto NeuroMaps list of maps or NeuroVault. And so that's another way that you could provide your data back to the community. And finally, if you're actually thinking of providing the MRI data itself, whether it's the raw data or minimally preprocessed data, you can use tools such as OpenNeuro. And make sure to check OpenNeuro actually, because it also hosts a lot of open data sets already there. So you might be thinking of a particular research that you actually realize, oh, they have interesting data about that research question on OpenNeuro. And another thing that you need to note if you want to provide open data to the community is to make sure that, first of all, you're abiding by any data sharing policies, particularly if you're using a data set that was previously openly available and you're deriving some phenotypes from that data sets. And you also need to ensure that if it's data that you have collected yourself, the ethics approval process has considered this possibility of providing data back to the community. So making your data open starts actually even prior to starting to collect the data. It starts at the level of like filling in ethics. To give you an example of such attempts, I I was involved in a research that we provided connectomes from the UK Biobank project back to the community. And the UK Biobank is famous for having a really stringent MTA. So it took us about a year after finalizing all our analyses to be able to actually share the data back with the public. And that was only through the UK Biobank's provided services. So this is something to consider and make sure that you abide by those laws or ethic rules. That being said, I also wanted to include a few different resources if you want to look into like how to make your data open. I thought there's the Brain Hack School Open Data module, which provides a lot of basic information and more detail than what I covered here for sure about open data. There's the particular tool called Data Lad that is really helpful if you are planning to access data from several large-scale studies. DataLad provides a solution that makes it easier to access those scripts, those data sets through scripts that make it more automated. So you can check out, there's basically a tutorial on the Brain Hack School on DataLad and how you could use it. And finally, if you want to use open data or provide your data back to the community, it's important to know a little bit about the brain imaging data standards, or shortly called BIDS, which is basically a set of rules on how you should store your data for others to know where to look for a specific file. Say if someone is interested to use only the resting state fMRI maps from your open data, BIDS provides them with a standard on where to look for the data that they're looking for. All right, so with that being said, I want to move to the next aspect of open science that I'll be discussing, which is open code. And open code is basically referring to the process of making your research analyses, be it scripts, algorithms, or software, available for others to use, inspect, and improve. And the main benefits of sharing code is, first of all, it will help others reproduce your results. And in doing so, it will definitely build trustworthiness. I personally, whenever I read a paper, the first thing that I check is obviously the figures and the results. Coming back to like Sid's comments, it's important to have nice visualization and ideally automated visualizations. But the second thing that I check usually if I'm interested in the paper is I go down to the very bottom section, look for code availability, and see if they have actually provided what they are basically claiming in the paper. Because after all, the way I see it, also, although a paper is still an academic work, it by itself is still kind of an advertisement of the knowledge that they have uncovered. And in order to be able to benefit from that knowledge, you actually need to have access to the code. Sharing code would also facilitate collaborations. In my own experience, like if there's an analysis that requires feedback from a few different collaborators, if you just send them a file and say, okay, this is my script, what do you think? This can get messy really quick. And there are tools like Git and GitHub that provide ways for online collaboration in a way that you can get comments from all different collaborators on the script that you're working on, but at the same time, keep track of the history and different versions of your code easily. Sharing code will also increase the impact of your research. As I said, people will like the fact that you are providing code alongside with your publication. And it will also save time for you and others by avoiding redundancy, in that even you, maybe 2 years later, you want to come back to a research that you did a while ago and you want to redo some of the analyses. And if you have already shared the code publicly, and it's hopefully commented well, it will even speed up your own future studies. So if you want to start working with open code, I should note that open code is not just for programmers, and code sharing can be done at basically different levels of analysis. Even if your research analysis is a very simple model that you think is like pretty straightforward, it uses very standard libraries like a linear model or an OLS, it is still beneficial to provide your code back to the community so that people can actually examine how the analysis was conducted. I would refer you to a tool called GitHub Gist, which basically requires minimal programming experience. All you need to do is if you have a script that you're already using with a specific programming language that you use for your analysis, whether it's R, Python, or MATLAB, you can just copy and paste your script to GitHub Gist, and it gives you a link. You can make it private or public. And when you make it public, everyone can see it. And the easiest way to make that open is to provide that link in your paper. However, if you have a larger projects, you might want to start thinking about using tools like GitHub and GitLab, which work on the basics of the Git framework, and that gives you the ability to do version management and control your script's transition and changes through time as you collaborate with others. And finally, if you have a larger project, usually it's worth developing it into a software or a toolbox. I'm sure most of you have seen a toolbox paper out there that has so many citations that is unbelievable that one single publication can get that many citations. And that basically shows that if you have a tool that you're developing and you think that others may want to use it, it's worth spending the time to develop an actual software based on that. Now, things to note when you want to work with open code is if you want to do automated version control, as I said, you need to start learning Git to track changes, and it basically helps you collaborate with others but know who changed what. And given that it's built for collaboration, it helps with things like code review, with feedbacks and bug fixes. So there are a few best practices that I would usually consider when I work with open code is, first of all, to include a README file within any GitHub project. Basically, by including your README file, you're providing a landing page to your research results, such that people who actually read your paper can click on your link of the GitHub repository and have a landing page view of, okay, what was actually done. So you provide a bit of explanation on how people could reproduce your findings. It's important to choose a license for your repository so that others know in terms of like legally what they can do with your code. Can they use it? Can they manipulate it? And how to appropriately credit you when they use your code. It's also important to try to get help from the community. So make sure to include a contribution guideline so that people know how they could provide feedback to your code. And don't forget to leave comments in the code whenever possible. There have been plenty of cases that even when I go back to read my own code from 6 months ago, I'm like struggling to understand what I did back then. And usually comments are the best ways to ease yourself into understanding your code. And it helps both you and others in terms of understanding the analyses later on. Now, I need to first of all, mention some of the challenges that open code usually comes with. It's first of all really time consuming. It can take time to clean your code and document it properly. However, if I were to give you some suggestions or solutions that would reduce the time required spending on making your code public, I would say that first and foremost, try to use standardized templates. I recently came across this tool, for example, which is called Cookie Cutter, that is really helpful if you're trying to package a Python code into like a Python package that could be simply installed with one line of code. It's also important to start building the Git repository early, so don't leave it for after the review process. Try to start it as early as the research begins. And usually a good practice is to first keep it as a private repository until the time that the paper is ready for publication. And that's probably the time that you want to make the code publicly available as well. But the Git repository should be sitting somewhere in your private repositories even before that. And as much as you can, avoid obviously reinventing the wheel. There are so many established tools out there, and in your scripts, try to use them as much as you can so that you write less code and it takes less time to prepare the open code, obviously. There's always the fear of criticism or errors in your code. Like even I have it whenever I'm like trying to provide some code publicly. I'm always worried that, oh, are others going to use it and then find a bug in my code? And uh, how is that going to affect my reputation? But at the end of the day, I would say it's really important to embrace open development as a learning process itself. The academic community knows that when you're providing code, you're actually doing a service to the community. So if I haven't really seen a case where people to try to destroy someone based on them providing open code. It usually is actually a way to reduce the chances of your research having faults or bugs in it. So if it's your first repository that you're providing, I would recommend asking a colleague or a supervisor to have a look at your repository, give you some feedback on what needs changing. And always keep this in mind that no code is perfect. And that's why we do open code practices to get peer feedback and improve our future works. And finally, the last challenge that I want to discuss is usually with providing open code, there's the concern of having to invest time on maintenance of what you're providing. And that can be the case, particularly if it's a software that you're providing. And one solution to reduce the load of doing that maintenance is to, first of all, collaborate with the community. So if someone, let's say on your Git repository, is posting an issue saying that, oh, I want to do this particular thing with your tool, but this feature is not implemented, you could actually have a guideline and tell them to contribute to improving the tool. It's really a community kind of environment, so you don't have to keep all the maintenance burden on your own shoulders. And even if you don't have time to spend on maintaining the code, look at it this way: simply making your scripts openly available is actually a significant advantage over any like other alternatives in which you keep your code to yourself, because at least people have a version of the script, even if you don't do any maintenance, that they could check and get some insights on what was actually done. So again, to refer you to some useful tools to check if you want to make your code open, I would recommend checking the Git concept. Git and GitHub are two services that provide basically platforms that you could use to upload your Git tracked code onto a public repository. If you're also interested and you think that there's value to your code by itself, apart from the paper that you're publishing, the Zenodo service actually has an integration with GitHub in which you could actually generate a DOI for your code so that people could also cite your code alongside with your paper. There's also Jupyter Notebooks or Google Colab, which are actually interactive environments where you could provide your analysis scripts, and it can have clear documentations along with the scripts, and people can use it without the need to usually install anything on their computer. And speaking of Jupyter Notebooks, they do merge well with this tool called Binder, which is yet another step in automating the process of reproducing your results for others, in that they don't need to install anything on their system, and Binder basically allows them to have a complete virtual PC somewhere on the internet that has access to the scripts that you've provided and can reproduce your results. If you want to check some helpful resources and learn more about these ideas of how to make your code open, I would recommend checking. There are plenty of amazing tutorials on how to use Git and GitHub, but I've pasted a single example here, which is from the BrainHack School, and there's also another more specific tutorial on how you could basically facilitate collaborations with Git and GitHub. And finally, if you're interested in if you're working on particularly Python scripts, and if you're interested in making it a software, make sure to check the last link there, which provides you some insight on how to create basically your first Python package. Now, that being said, I'm going to move to the next topic, which is open access publishing. And as you know, this may be the elephant in the room. Whenever we talk about open science, there's the concern of, okay, where do I publish? How do people see my publication? And thankfully, so far, things are going to the right direction. Most journals are now providing open access solutions that can help you make your research articles freely available to everyone online without having to pay to access your paper. Obviously, there are many benefits to making your paper open access. It will increase the reach of your results, increase your citations, and actually many funders actually required to publish in open access journals. However, there's the culprit of the common form of open access that is currently being provided, which is called open access, which basically the researcher has to pay for that. And that kind of is out of your hands sometimes. It depends on whether you have enough funding or not. An alternative to gold open access is something that is known as green open access, which I would like to suggest as an alternative solution, which is basically you can upload a copy of your work. Usually this is the pre-acceptance. It's not the preprint, it's after review, but without any editorial final proofing and things like that. And you could provide that version of your paper either through things like GitHub pages or ResearchGate so that others can read your paper without the need to actually having to download it from a publication site that is sitting behind a paywall. And finally, another closely related thing is to try to promote pre-printing. So putting up early versions of your work up on these servers that provide them freely to the public to check out. It helps with fast dissemination of your results. People see it early. People give you feedback early, which could actually even be helpful in the review process. You can some sort of establish the priority of you being the first person doing that particular research, and it obviously promotes open accessibility. There are many preprint servers out there, but if you're at the stage of publishing your paper, probably a good idea to check some of these preprint servers and choose one to put your data on. I would next like to talk briefly on open infrastructure. I won't invest too much time on this. I know that Steffen will cover a lot of interesting ideas with regards to open infrastructure, but basically open infrastructure is when we use tools and platforms in a way that we make it available to everyone. And these tools could be open compute resources, storage solutions, and data sharing solutions. Particularly for those who are doing neuroimaging research in Australia, make sure to check the ARDC services provided by Nectar. Nectar provides virtual desktops, Jupyter notebooks, Binder Hub, and GPU resources. I think it's pretty much free as long as you have a research proposal in mind. And the one that I particularly used in past is I tried running a virtual desktop that has a Neurodesk on top of it. So basically you have all the software you need ready there to be used. I'm sure Steffen will go into detail about how you could use Neurodesk. And finally, I wanted to say that there are a lot of open educational resources out there. So while these ideas of open science might be new to you, there's a vast amount of information out there that could help you learn and implement open science practices in your own research. Four main places where I can think of providing educational resources is the BrainHack School, the NeuroHack Academy, NeuroMatch, and Open Science MOOC. Make sure to check out those websites to find out more. And actually, if you're interested in investing a little bit of more time on these kinds of courses, I noticed there's an upcoming NeuroMatch course on Open Science 101, which is the Asia Oceania section is in late October, and I think registration is still open. So if you like to spend a week on learning different aspects of open science, make sure to check out this course. Okay, so finally, some closing remarks. I would like to say that open science is actually best done in a community. It helps you build collaborations and networks. So I would like to encourage you to join open science communities around you to learn and learn from the community, and also find mentorship and resources that could help you in your path to practicing open science tools. So a great example of that within human brain mapping is OHBM's Open Science Special Interest Group. Make sure to check out their website to get to know what kinds of works they do. They usually run hackathons every year. And if you attend the OHBM conference, there's usually this parallel conference called the Open Science Room that happens in the same time, which you may want to check out. Finally, to leave you with some take-home messages, I think open science can be done in small steps that make big impact. So don't try to look at it as an all or nothing. I'm either going to implement all these different principles or I'm not going to touch open science. You can start small, step by step, build your experience with using these principles. And it does include a lot of effort, but usually the effort pays off. And I would say it is worth the time that you put on it. And interestingly, it gives you skills that are helpful beyond academia. For example, if you know how to use Git or GitHub, I'm sure there are a lot of industries out there that would value such skills. So even if you're not thinking of staying in academia, think of open science as a way to learn new things that can be helpful in the future. All right, so I think that was pretty much it. Thank you for your attention and happy to take questions at the end.
Great, thank you, Sina. All right, so thank you for that talk. Lots of useful resources. So I think if you're happy to share your slides at the end, we can circulate that through the rest of the emailing list for the attendees, which is very useful. Thank you. So now we've got Dr. Steffen Bollmann. He's a senior research fellow and leads the computational imaging group at the University of Queensland. And his work has developed methods to integrate multiple imaging modalities to allow for a better understanding of structural changes in the brain and across neurodegenerative diseases. And he's also worked a lot on developing open source software for neuroimaging and neuroimaging analyses. And he's going to be presenting on that, going from the open data all the way through to open analyses using his software Neurodesk.
Thank you for this kind introduction. Can you see my slides?
Yes.
Wonderful. Okay, cool. I just have to intervene. It's not my software. It's a big community project. I will highlight that in a second. But yeah, I wanted to start with a big thank you to the Australian community because the Neurodesk project by now has over 221 monthly users just from Australia alone. So we just have roughly about 1,000 monthly users from across the world, but you see a large proportion is coming from Australia. And that really shows that open science has a really high value here in our community. And considering that only the United States is on place 1 and Australia is place 2, Australia States has a much bigger community, is much better funded than Australia. This really shows what a special community we are here. And I think also this turnout in the webinar today shows that we really care about this, and it's great. And yeah, just correcting that Neurodesk is not my project. It's a big project that we started with a lot of people here in Australia. They're highlighted here in bold. You see there's a high geographic bias to our project. We got funding from the ARDC in 2020 to build out the project. And we have lots of supporters from across the world, including the big cloud providers like AWS, Google Cloud, Oracle for research, and research cloud providers like Jetstream, EGI, Nectar Cloud in Australia. And we're supported by the OHBM and by the National Imaging Facility. So thank you to all who contribute to Neurodesk, who support Neurodesk, and who use Neurodesk. So I want to start with why we build Neurodesk. And maybe not everyone here has heard about it. So I quickly want to show what the problems that we're trying to solve. So the first one is really non-reproducible workflows, right? So when you work across different operating systems, different computers, different labs, what can easily happen is you run an analysis, and you run it again somewhere else and you don't get the same results. And the problem is really that software has dependencies, software dependencies. These do very critical functions in these tools. And when they change, they will create different results. And this is really annoying, and it can even lead to significantly different results, as shown in this one study that we have here on the slide. Then we also want to run these analyses on different computing infrastructure. So we want to run it on our notebook, on an HPC cluster, on cloud resources. And the challenge is that we always have to reinstall software on these systems. And that connects to my point one again. If I have to reinstall and I'm getting different results, well, what's the use of that? And it's really, really hard sometimes to install software on HPC clusters. Then also data management. How do we manage data across different institutions? BIDS, for example, was already mentioned earlier. So it's a really cool standard for organizing your data. But then the challenge is you still need to do it, and the tools are not always available easily, and there's still a lot of knowledge required. So we wanted to make all of this much easier. And then also sharing data and using open data. So I will show this later in the talk. And then data storage and privacy, right? So how do we deal with private data that's not open data? How can we analyze this nicely? How can we share analyses with our collaborators without sharing the data? So we wanted to solve these problems all in one tool. And this is what we built. It's called Neurodesk. You see, it's really the core of this is the community. We have a Neuro containers repository where we collect all tools. And then we have lots of interfaces how you can use these tools. So I'll start with Neuro containers. Neuro containers basically is just all the tools that you can imagine: fMRI prep, ANTS, Field Trip, RStudio, packaged in software containers. So what's a software container? Think about a lunchbox. A lunchbox, you can put your food in and then you can stack them in the fridge and nothing gets messed up and everything stays where it is. And that's really what a software container is. It just contains the software, all dependencies like Python, Conda, all applications, Visual Studio Code, and all binaries and libraries that this software needs. So this means when you have it in a container, you can take it and can move it somewhere else. That's basically what it is. And then we build an accessibility layer to make using containers really easy. Because if you've used containers in the past, you probably know there's a lot of things to think about, like Docker, Singularity, and Aptainer, and different formats and different files. And it can be really confusing. So we just made this really easy. There's just one way in Neurodesk to do it, or there's multiple ways to do it, but it's all really consistently presented to the user. So quickly looking into a bit more what containers are. So when you look at how an operating system works, is in this case, we have Ubuntu 20.04, so it's a Linux operating system. And then let's say we have a software called MNE. And this MNE software depends on Python, which again depends on multiple binaries and libraries, which often gets installed by Conda. And then we have VS Code to interact with this. So now when we update Ubuntu, what happens sometimes is that these binaries and libraries break, and it could happen that Python doesn't work anymore. So probably people have been in this space. And also this means that we can't just take this and move it to another computer. If this computer doesn't have Ubuntu 20.04, it won't run. And this also means when you upgrade, you get problems. So this is what a container really helps with. It basically takes everything that the software needs, packages in a box, and we can take this box and move it anywhere. And the cool thing is we can also take lots of these different versions of these tools. We can all put them in separate boxes and we can have them installed on the same system, which is usually not that easy because different software versions often have different dependencies. So what can sometimes happen is you can't install different free server versions on the same computer because they will have different dependencies. That means it's impossible, basically. When you put them in a container, it is possible. And that's why we went down and implemented these containers. And then the cool thing is what also containers can do is they can run on any operating system these days. They are a native function of Linux. So if you run Linux, it's a kernel feature and it just works. If you run Windows and Mac OS, there's some virtualization involved, a little bit of a performance penalty, but it's really well implemented these days and just works. So that's a really big benefit what containers can do. We can store these images in registries, make it nicely available. So there's lots of cool things that containers can do. And then what we did with it, we have basically two ways of accessing these containers. We first have an interactive desktop, which we call Neurodesktop. This is a browser-accessible virtual desktop that runs on Linux, Windows, Mac, cloud. And then we have a command line interface that we call NeuroCommand. This is great for high-performance computing clusters where you don't have a desktop. And it's also great for Jupyter notebooks where you also don't have a desktop or just simply your command line. And then you see this little script that's jumping between systems. That's the same analysis. And now the cool thing is what we can do in Neurodesk is we can write an analysis on one system, move it to another system, and it will behave identically wherever you run it. And this is really cool. This wasn't possible before Neurodesk. I will show this later how this looks like. So now we have two big ways of how you could use Neurodesk. So the first one is a central instance model. So this is commonly used for workshops, for teaching, for training, for hackathons. What we basically do is we install a Neurodesk on a server, on a cloud instance, or on a university resource with shared resources. And then every researcher logs into this central system. People can collaborate on that, they can code together, they can work on the same data. It's fantastic if it's not really private data. This is a great model. If it's open data, this is a wonderful model that lots of people use worldwide. The other model that we see commonly is private data, sensitive data, patient data that's locked behind institution firewalls. That's not difficult. That's not easy to share. And then what we do there is a federated instance model. So basically every researcher runs Neurodesk on their institution. They all analyze and they can all run the same script on their data, and then they can aggregate results on a higher level. So this is, for example, Enigma style studies where we pool information on a higher level. But both of these models are very common and work really well depending on the data that's involved. So I want to come to this open data workflow in Neurodesk. So how does this look like? So first, I'll start with importing data, and Neurodesk is very flexible there. We basically support anything that's out there. So you can import your data directly from the instruments. We support DataLab, which was mentioned earlier. It's a great tool to download data from, for example, OpenNeuro, but also lots of other resources. We have the OSF client installed, so you can pull data from OSF with a few commands. You can pull data from XNet, which is a server that hosts DICOM data. And we can also support any cloud interface that's out there. So then we can process the data. And we have currently more than 100 tools available in Neurodesk. So here I just listed a couple, but M&E, FSL, Brainstorm, Field Trip. So it's not just neuroimaging, it's also electrophysiology, because that's how Neurodesk was funded in the last years, to build actually a new electrophysiology platform for EEG and MEG data. Then we can organize this data, for example, in bit structure or the output of our analysis. We can organize this in bits. We can document our analyses. And for this, we also heard these things earlier in the talks. We support bits and Jupyter, and we have lots of tools to help people to get their data into bits. And we have lots of cool tools to make working with Jupyter notebooks very nice and easy. And I will show that later. And then finally, we can share that with the community. So we can upload our scripts to Google Colab, and everything you do in Neurodesk runs on Google Colab. We can upload data to OpenNeuro. Again, we support DataLab to push data out to OpenNeuro or to OSF. We support GitHub and OSF and yeah, lots of other platforms. These are just a couple of examples. So today, I thought I'd pick a very simple example and I'll show what we can do in this life cycle. So what we will do is we will pull an open data set from OpenNeuro using DataLab. We'll analyze this data with FSL. We will do all of this in a Jupyter notebook. We will upload this notebook to Google Colab and show that it runs there as well. We can share it with our paper, for example. And then I will show to upload this on GitHub and share the notebook on GitHub and the code. And then I will show how we can upload the data that we produced, the outputs of our analysis, to the Open Science Framework OSF. And then someone else can take over and use what we've built and build their analysis on top. And just to quote an earlier speaker here, live demonstrations are a really bad idea. And I fully agree. It's a really bad idea, and I'm full of bad ideas. So I thought, instead of just showing you slides where everything looks fun, I'll just fail catastrophically and show you how bad it really is. So the best place to start with Neurodesk is our website. So our website lists how you can get started with Neurodesk. Neurodesk runs on pretty much any system you have available. It's very, very flexible. So you can run it on your local PC, on Mac, on Linux, on Windows. We do support even ARM on Mac. It can run on HPC. It can run on cloud. It can run on Google Colab. We already heard that it can run on the Nectar service. So if you're an Australian researcher, you have an AAF account, you can get free cloud resources on the Nectar service, and you can run a full desktop with Neurodesk and everything available with free storage, with free compute, and you can do your analyses on there. It's a fantastic service provided by the ARDC in collaboration with us. What I want to show today is I want to show a service that's really useful if you don't have really a lot of affiliations with universities. We call it the place service. And you also, let's say you don't want to install anything on your computer. So if you want to run Neurodesk on your computer, you need to at least have Podman or Docker installed. These are tools to run containers. And if you just use our place service, we have 3 different locations. You don't need to install anything. It's hosted on the cloud. It's provided by different services. So for example, in Australia, it's provided by AIDC, in the US by Jetstream, in Europe through the EGA Federation and CESNet, which is a Czech provider, a cloud provider. And I'll pick the Australia server. Since this is AIDC resources, it means we're not allowed to provide resources to anyone. We're only allowed to provide resources to Australian researchers. This means you have to authenticate with an Australian university. So as soon as you have a university account, this should work. And then we can start a Neurodesk environment on here. What I also want to show is OpenNeuro. We heard OpenNeuro earlier in a talk. It's a fantastic website and project run out of Stanford, Russ Poldrek's team. And they currently have 1,190 public data sets. And what I do is I'll just search for a flanker task that we could analyze. And what we can do here is we can just look up this data set. So we see what's roughly in there. We see what a task description is. We see the data. And then here we get a clone link. And this is a GitHub URL. So what do you do with this? Let me quickly show you. So I'll grab this URL. Yep. So you can click on this copy link or just this one. And then we go to Neurodesk. So by now, Neurodesk started up in the back end. And what you will see right away is it's just a Jupyter Notebook interface. And we did this on purpose. We wanted that people have a familiar interface and that they're not shocked by anything new. And we also have a full desktop. So I'll start there. So this is our new desktop interface. So you can open that, and then you get a full Linux virtual desktop that's integrated fully into this Jupyter Lab system. And this takes a couple of seconds, but once it's there, you will see a couple of things. First, we have a standard startup menu here. So here we have all the applications that are included in Neurodesk, and there are a lot of them, and we're continuously adding tools. So pretty much every day there's a new version or a new tool that's being added. And also here, FSL, we have lots of different versions, and this is impossible without Neurodesk. You can't install FSL 603 and 6078 in the same system. They have conflicting dependencies, but because everything for us is a container, we can do this. So what you could do is you could just load FSL in here, and then you could run your bet, and then everything is fun. So yeah, you can run your interactive analyses here. But what I want to do now is I want to download this OpenNeuro dataset. So what we have done as well is we have integrated DataLad already. And DataLad is a fantastic tool that also was mentioned earlier. It has a command called DataLad install. So you install a dataset, and then you just paste this Git link that OpenNeuro gives you. Now, what this will do is it will check out this data. But now you would say, man, this can't be, right? This is a huge data set. This was really quick. And yes, you'll see here, it's only 1.7 megabyte on disk. And the reason is it hasn't actually downloaded the data. This is just the metadata. And when we go in here, for example, subject 8, anatomical scan, we see there's just a link. The data is actually not there. In order to get the data, what we need to do is we need to run another command. And it's called datalad get. And then we need to say what directory or what file we want to get. So here I said, give me please subject number 8. So what this is doing now, this is pulling data live from the OpenNeuro repository, which is in the US on AWS, and it will pull it down to our Australian server currently running here. So this is now being done. When we now reload the folder, we see suddenly there is a subject 08 NIIGZ. When I double click this, we will open automatically a fantastic tool developed by Chris Rawdon, MRIcroGL. It's a fantastic viewer, has lots of capabilities. And we can quickly check, cool, it's an anatomical scan. Wonderful. What we can also do is, it's always good to have a look at your functional data as well. So we can drag and drop this data in here. So we see, okay, well, this looks like a flanker task, right? Obviously, something happened in that brain, and it looks like we have some data. So that's great. I guess we can continue. So as I said, what we could do now is we could just open FSL. So I showed we can do this through the command line, through this menu over here, but we can also do this programmatically, which is of course a lot nicer, right? If we can program it, it's more reproducible. So if I just type bet on the command line, it will say, oh, this command doesn't exist. The reason is in Neurodesk, you have to be explicit. So what you should do is you should say, I want FSL in version 604, for example. And now if I run bet, I'm getting bet. And if I'm asking which bet am I executing, I'm seeing that I'm executing it from FSL 604, which was built on a specific day. So cool. Now I could write a bash script and I could actually analyze my data. However, bash scripts are good, but notebooks are a really fun way to analyze data and to visualize data. So let's look at this. So for this, I prepared on GitHub, on my account, I'll just prepared a little demonstration repository. As we heard earlier, having things on GitHub is great, and starting with a GitHub repository before you start the analysis is even better. So here I have a little example notebook where I just have a couple of commands. So the first one is I'll install Neurodesk on, for example, Google Colab. So this is just a standard cell that we have in there. I output what CPU I have, and then I download the data, I visualize it, I analyze it, and that's it. So what I can do with this now is I can, for example, I can run this in any system that supports Neurodesk. So I can take this notebook, I can run it in any Neurodesk system, or I can run it on Google Colab. So let me quickly show you how this would look like, because it will take a couple minutes on Google Colab. So Colab is a fantastic tool. It's provided free from Google. So you can just grab a file from GitHub, for example. And then I can just say run all. And on Google Colab, what will happen now is the first cell will install Neurodesk. This will take about 5 minutes on Google Colab. And then it will download the data on Google Colab, it will visualize it. And once I'm done demonstrating doing this on Neurodesk, we can then look at the output here as well. So now let's keep going on Neurodesk. So what I want to do is I want to show you now how to link Neurodesk to a GitHub account. So the first thing we need to do is we need to tell GitHub that this is our account and we can talk to GitHub. The way we do this is we have an SSH key, which is in the IDE rsa.public file in the SSH folder. And it's just this long list of letters and numbers. And what we need to do is we need to go in our GitHub account under settings, under SSH and GPG keys, we need to add a new SSH key, and then we can just edit. Then it will ask us if it's really us doing this, because with this key, anyone can do anything on our GitHub account. So we want to be sure that this is actually okay. And yep, this key is now added. What this means now is that this Neurodesk instance, and when you have Neurodesk installed on your computer, you only need to do this once. If you do it on a place server, of course, the place server is only temporary, so you have to do it every time. What I can do now is I go back to this repository. Nope. Here it is. And I can check out this repository on Neurodesk. For this, it's important to take the SSH option, not the HTTPS option, because that's how we set it up now. Oh, don't need a desktop anymore. I close this one. Then we do a git clone of this repository. So the first time we're doing this, it will ask us if we really trust that github.com is behind this domain, because it can't verify that this is the case. And then this repository is downloaded. So now here we have this OHBM Austria directory, and here's our example notebook. So as I said earlier, this first cell doesn't do anything on Neurodesk because it's already everything is set up. It's always good practice to output what processor you're running on, because Neurodesk only controls software dependencies. We do not control hardware. So if you run this on an AMD processor versus an Intel processor, you might get different results. It's very, very small, the differences. And we show that in our Neurodesk paper, how small these effects are, but they do exist. Then here, we're downloading the data. So same thing, with data let install, we go in the directory, we get our subject date. And then we use a really cool functionality. It's a fantastic toolkit developed by Chris Rawdon, Taylor Hanaik in the US, and lots of other people. It's called NeView, and NeView is a fantastic library for visualization. It's not yet as programmable as probably Sid would like to have it, but they're working on it. So very soon, there will be a way how you can store a view even, and you can actually have and program it completely from this. So you can actually write in your code what it is. Currently, it's an interactive viewer, and I'm just using it at this. So here it's just cool. I can quickly look through it. I can see, wow, it's a full brain. It has a skull, and that's really great. Now, the next thing is, I said earlier, if you want to use FSL and BET tool that comes in FSL, I need to load it. Everything in Neurodesk, you need to be specific about it. So we have lots of tools available. So you can, for example, see, I want FSL, and here you see the different versions of FSL we have available. So what we need to do is we need to say import lmod and then load FSL. And now, once we did this, BET will be available, and it will come from FSL 604. And what I'm doing here is I'm taking the anatomical scan of the subject, I will skull strip it, and I get a brain output. So let's see if this works. So this will take a couple seconds, but theoretically, if this works, here is now our subject brain NII. And it's always good to check if it actually worked. So here I'm just visualizing exactly that file, and here it is. So yeah, that's our simple analysis, right? Very cool. And what I can do now is I can say, oh, okay, I'm happy with this. Let's commit this back up to GitHub. So we also have Git integration in here. So what we can simply do is we can say our example, iPine notebook. Let's take this and say analysis done. And there it is. It's committing changes. And then we can push this up to GitHub so everyone can see it. And then I will quickly show how this looks like. So here we are. Now I can refresh this here, and I see my commit analysis done a couple seconds ago. I can open that notebook on GitHub. I can look at it. I can see what exactly I have done, what the outputs are, and how it looks like. Only problem right now is it doesn't store the output of this new view because it's an interactive viewer. As I said, there will be a functionality hopefully soon that allows storing a snapshot, a programmable snapshot of your visualization as well. But there are lots of other ways how you could do this right now. And quickly just coming back to the same thing that I run on Google Colab. So on Google Colab, we're running on a different processor. It's an Intel Xeon 2.2 gigahertz. But otherwise, everything ran identically. So DataLab ran, downloaded the data. We visualized the data here. Since I'm zoomed out a little bit more, I'm also getting a 3D rendering of the brain, which is really cool. It looks like they did a good job with anonymization here. And then the brain extraction ran identically. And here it is. Here's my brain extracted scan. And I can also check this on a 3D view. This looks pretty okay. It actually did a good job, which is rare for BET, but sometimes it works out of the box, which is really cool. I didn't have to tweak any settings there. So this is really cool, right? Because this analysis I can now attach to my paper, and I can say, reviewer, please go and execute it. And the cool thing is also people can reuse it and change it and play with it and find bugs. And I think this is really cool. So the last thing I want to show now is I want to show how to upload this data to the Open Science Framework. So this was mentioned earlier. Open Science Framework is a fantastic initiative which around Brian Nosek and people. And what we can do here is we can create a token. A token is similar to this SSH key system that I had earlier for GitHub. It's basically here in personal access tokens. You need to create a token once, and then you get a long number of strings again. And then we can use that to authenticate to OSF from Neurodesk. So what I will do is I will create a new project, and I'll call that OHPM webinar. Create, go to new project. Because what I need is I need these couple of letters up here. This is my project ID. So what I can do now is I can go in this directory. So OHPM is an example. And here, let's say I want to share this brain data set with OSF. What I have to do is I have to say OSF init, So this will initialize a project for OSF. I need to provide my account name. And then I need to provide the project ID, which I just created. The other thing I have to do is I have to give it that token. Just in order to not reveal my token to you, just for security reasons, I put it in the file so you don't see it, but I'm just sourcing that file, and then this means the token is set. What I can do now is I can now upload anything to the OSF from the command line programmatically. And of course, I'm just showing this with one file, but you can do this with thousands of files. So I'll take the subject file and I say, name it exactly the same way on OSF. And this will take the file, upload it to the OSF. And I will do the same thing with the notebook because it's nice to have to see how the data was created. So I'll take this as well, put that up. I need to add the upload command as well, OSF upload. I'll put that up to OSF. And when we now go to OSF here and refresh this page, what we see here is that now we have the subject 08 brain scan. We have our example notebook, so we can even click on this notebook. We can render that on OSF, so we can see exactly what analysis has been done. And we can even pull the whole project, get the outputs. So we can either choose to run it again, or we can just take the outputs and check if it makes sense and go from there. Okay, this is really everything I had in mind. So as we saw, live demos are a bad idea, but sometimes they work. But yeah, with this, I want to thank you for your attention. So I want to finish with a really important message is Neurodesk needs you. So currently people come to me and say, can you add these 1 million of tools? And no, I can't do it alone. We need you. We need your help. If you have a tool you want to get on there, please help us to do it. We are underfunded, we are understaffed, and we're overworked. So we really, really need your help. It is an open source project. It is a community project. So if you want to help, please get in touch with me or with anyone in the team. So with this, thank you very much. And I'm looking forward to your questions. Thank you.
Amazing. Thank you, Steffen. That is very impressive. And congratulations on doing the live demo successfully. I think there's quite a lot of questions in the chat, actually, especially in relation to, yeah, like pretty much all the first 5 questions, I think, are directed to you, Steffen, for the Neurodesk. Can you see the questions on your panel?
Where do I see them?
So if you look down the bottom, there should be like a Q&A pop-up where you can see like messages that have appeared.
Oh, yes, found it. Okay. Okay, should I just go through them?
Yeah,
okay.
I think so.
Trang Sao asked, can we request new software to be installed on Neurodesk? Yes, you can. I'm not sharing the screen anymore. If it's okay, I'll just share the screen again so I can quickly show this. Okay, so I'm sharing this again. So yes, exactly. So before you ask, obviously have a look if we have it already. So here we have application, we have a whole list. So if you search that, you see what we have installed. Then yes, the best thing for us is if you help us. So we have a developer documentation where we say, how can you add new tools? So we have a description here, and then you can open an issue, and then we can integrate it. Yes. But as I said, we're very limited in people power at the moment. So yes, the more you can help us, the quicker it is. How much space can we, that's the next question from Trang Cao. What is the best way for people without uni account to use Neurodesk? Oh no, wait, sorry, I skipped one. How much space can we use to download data in Neurodesk? Okay, so if you run Neurodesk on your own computer, you can use as much space as you have on your computer. If you use it on a university resource, same thing. The university will restrict what you can do. If you run Neurodesk on the ARDC Nectar cloud, you have 50 gigabyte. If you run it on our free resources, we restrict you to 2 gigabyte because we can't handle the costs of having thousands of people dumping data on us. Our cloud bill is already quite high and we need to get it down. So we have to limit these things, what we can do there for free. But yes, if Yeah, basically the sky is the limit. Whatever you can pay, you can do it. So we have had installations of Neurodesk in the US. They had multiple 100 terabytes of data on there. It's not a problem. It's just the backend storage that needs to do it. So then another question from Trankau is, what is the best way for people without Uni account to use Neurodesk? Installing it on your computer in Docker and Podman, or using our free Neurodesk Play service. There is one service that's currently open. It's the US service that's running at least a GitHub authentication. The European service doesn't need any authentication right now, but we might change that in the future. Ella asks, Neurodesk is fantastic. Is it possible to request more modules, containers? If so, how long do they take to implement? Yes, same question as earlier. Yes, it's possible to request these. Depending on how long does it take to implement, it depends on how difficult it is. It depends on how much help we have. If you can send us a recipe that works, it's a couple of minutes. If there's no help, it could be days or weeks, depending on our workload, because we're doing this in our free time. Yeah. Is there a way to transfer the data from Exner to Neurodesk? What is the data storage limit for each user? So yes, you can transfer data from Exner to Neurodesk. So you can have a Neurodesk, you have an Exner plugin, an Exner tool that can interact with your Exner instance, and you can download the data. Again, same thing. What is the data storage limit? It depends on what limits you have applied. In our free instance, it's 2 GB. In ARDC Nectar, it's 50 GB. But yeah, it really depends. I think that's all the Neurodesk questions. So yeah, I'll unshare and leave the stage to other people. Thank you.
Thank you. And so sort of the next question is more of a like discussion question, I guess. So how do we ensure that ECRs are trained in the best practices for data and code sharing? And do you think this should be implemented specifically within like research institutes that are training PhD students? I mean, I can give like a general answer to that. As like a semi-recent PhD graduate, I feel like there should be courses within the research institutes that like encourage students to do this, especially early on. I know I basically learned how to get better at coding and using GitHub way too far down the line into my PhD. So yeah, I think that would be a great way of doing it. But as Sina mentioned, so we've got a couple of open data schools that people might be able to enroll in. So hopefully there's sort of more sort of online-based training tools that we can use to get there. And then a question for Sid. So Josh said, thanks to all the speakers. Sid, could you provide more details for embedding figures in code for figures in journal papers? Are we supposed to ask the journal to do this, or is it how we upload our manuscripts?
Josh, this is incredibly journal specific. So at the base level, journals can allow you to have a supplement of rich media, so you can just upload an IFTY file, but at a richer level, neuroimaging journals will have built-in like Nifty viewers, so you can upload it there. The ultimate level, which I think only Aperture Neuro and maybe F1000 and eLife do, is you can upload an HTML version of your paper where these kinds of viewers and interactivity, even just GIFs like I was showing, are built in and embedded into the paper. So it's incredibly journal specific as to what's available.
Just to add to what Sid said, I also wanted to refer people to this new resource called Neurolibre, which is basically a preprint server, which I believe kind of supports like these interactive code environments. So basically you have a preprint that actually has an HTML version in which you could insert interactive elements. So that might also be something interesting to check out.
Yeah, I just put the link to Neurolibre there for people to look at. It's a really cool resource. I haven't used it personally, but it's lovely to go through and explore other people's work on there. So hopefully it will build momentum and more people will start using it as well. All right. Does anyone have any remaining questions? Oh, yes. can we access LC model on Neurodesk, and is there a license for its commercial use?
Yes, LC model is on there, and LC model is not commercial software anymore. Stephen Provenger retired 2 years ago, and he released LC model as open source fully to the world. If you want to read the code, it's fantastic. And it's on Neurodesk, and it works really well. We have lots of LC model users on there. So yeah, please go and use it. It's fantastic, but it will not be developed any further. So it's basically what Steve Provenger released to the public. I don't think it will be maintained by anyone because the code is really hard.
Great. Thank you, Steffen. Any last remaining questions? All right. Well, I think that's probably, every time. Oh, there we go. Thank you. I thought it was a question. So yes, thank you to the panelists, Sid, Sina, and Steffen for your wonderful work in presenting. This will also be recorded, so we're going to upload it to YouTube if all the panelists are happy. So we can sort of use this in future for people to look back over, and we'll send through sort of a circulation of a couple of the different resources that were mentioned throughout the talks today to everyone on the OHBM Australia mailing list. Thank you.
Thanks, everyone.